Come on. Nice. This is the one my daughter would predict all the time. Would pick, I mean. Rainbows. Okay. So we got DC circuits and resistors. So we have some intro and background. So let's think about this. Yeah, so we have, yep, I can think of a great way to get started is batteries and power supplies, generators, like the Hoover Dam. Generate electricity, blah, blah. But remember, the bottom line is that they produce potential energy, which is PE per charge, right? Which is defined as voltage. And then we then use that energy to do useful things like heat, light, whatever. And the things that do the useful things for us can be represented as resistors. Remember, we had this discussion last week. And something like, to get to do this, we need a thing called a circuit. And so we will present we're going to show a brief description of circuits. Give me a minute. Yeah, brief description of circuits. And we need a thing called a circuit, and then the circuit is going to include power, the power supply or the battery, and it's going to include our resistive things, our resistors or resistive things, and there's various types of circuits. Various ways to connect them together. So we're going to present a brief description of circuit theory. And then we're not going to derive the rules of combination. We're just going to use the concepts to justify the rules of combination, which says that in a series circuit, the current's the same everywhere, so the voltage change across every element has to equal the the power supply. So this allows us to say that in series resistors go as R1 plus R2 plus R3 to justify the rules of combination. Don't want you to read, I don't want you to derive it. Don't just copy what's in the lab manual. That goes into your log book. Rules of combination. We will then, let's see, is that it? Right. Justify the rules of combination. We will present the results of a series of measurements using, what did we use? One, two, we had the first, one, two, three, four different circuits, four different circuits. And it's up to you how you want to maybe list it. Wait, here is where that goes. We will present. And I like making my own little kind of bullet points here. Oh, brief description, that's the same bullet point. Let's see, get that out of there. Yep, and there's another one here. All right. We will, we will also present a brief description of, Deborah, this is the report up here. But yeah, all the analysis for this and the stuff, this is just, I mean, I'd like to see this description in today's notebook, but the work itself is the final notebook because we're running out of time. It's already overtime. And this is, I'm outlining the report for you. I said I would. Good, all right. A brief description of analog meters and results of a study of meters, right? That was results of a study of meters. Yeah, okay. Yep. Oh, no worries, Deborah. You guys, you need coaching on this sort of stuff. Okay. And then now let's see. We got the intro. So what did I say? This is more like an intro, I guess, advanced organizer, right? Intro organizer. And then now we get into the part about circuits and the circuit theory business, but really minimal, and how you use it to do the rules of combination. Then some lag. And so let's go background. And so today, yeah, exactly. Yeah, that's exactly right, Sarah. Oh, yeah, of course, of course. You're welcome, Sarah. I'll post these notes in the next day or two. Welcome. Oh, that means you're done, Carla. Okay. Right. So this is where you do the circuit theory explicitly, right? The rules of combination. And really, the biggest thing from the circuit theory is to like you just draw the you present the series circuit, and then you have the three rules, right? One conductive path, current is the same everywhere, and three, the voltages add up, right? In parallel, multiple paths, the currents add to the total, and the voltages are all the same, right? And then you say this allows us to say that since the voltage drop is equal to IR and I is the same for everybody, this allows us to say R equivalent equals R1 plus R2 plus R3. Then what else? Oh, this is when you describe the meters. And remember, there is current through, voltage across. This is very, very important. So that means that ideal is our ammeter equals 0 and our voltmeter equals infinity. What else? Oh, right. And this is where you'll see, and that has to do with why we saw that discrepancies in, and I just I've told you, I'll remind you that our analog voltmeter is generally about 10K, and our digital voltmeter is generally about 10 meg ohms. But this you save this for later when you're analyzing the part one data. Describe meter. Yeah, back. What else did it? I think that's it. And then procedure. Now, guys, don't. I saw a couple reports where people were going like step by step. You're not doing that. You're saying we set up 4 circuits. Here's circuit 1, circuit 2, circuit 3. 1, 2, 3, 4. And use the device under test, right? Don't draw. We measured, for the first part, we had the power supply. We had the ammeter here. We had the device under test, and we had either an analog voltmeter or a digital voltmeter. We measured the current and the voltage across the three resistors for each one. Here is our table. Or, well, not yet. That comes a little later. Or you could say results in table 1 later on. 2 is the series, and we set up this circuit, and we took these measurements here. I suppose you could put objective is to verify. Well, that's what you know. What you say? Procedure 1 and 2. We want to verify rules of combination. Oh no, excuse me. This is part 1. That's for part 2 and 3. That's it. Part 1 is properties of meters. Oh, I also forgot about Ohm's law. Oof. And right? We have to get Ohm's law here. This is super important. Just say we have a basic relationship, and then, yeah, even before circuit theory. Come on, I'm lagging again. Uh-oh. Okay. Ohm's law. Holy smoke. All right. And you remember I talked about power, I talked about different things. Up to you what you think is important. Just don't do the kitchen sink, right? So series and parallel. And then the mixed. And you can make that diagram and say that we took, we made current and voltage measurements as shown in this diagram. And we compared predictions to measurements. And try to stick into that. Well, the predictions are where you say, look, we have the circuit theory, we have the rules of combination. All of these things have been turned out to be true in parts 1, 2, and 3. And so now at the end, we are going to use all that information to predict that this current and that current will have this relationship, and this voltage and that voltage will have this relationship, this other relationship. And we went ahead and measured it. And if you see this table, and here, like, all right, so V1 plus V2 should equal V3. And you see from the table, yes, it does. And you point to the exact place on the table. Okay. Wow. We're really over time. I will, excuse me. I'm going to slice and dice the video, the recording for just this last part so that you don't have to go through the whole Zoom recording. I'll post these notes as well in the next, I didn't take screenshots. So in fact, I went slowly. So the other stuff, yeah. All right. Yeah, I'm sorry. I'm burning. I'm tired. I was feeling like really Mondayed out at the beginning of class. I feel better now. And thank you guys. I hope I've given you some energy and you've given me some energy for sure. All right, guys. So don't, bug me. Ask questions. Okay. Several people are. Stay safe. I guess you got to go, right? So I'll see you all soon. Take care of yourselves. All right. Save. Save. See you later, guys. All right. Ooh, what is this? See you, Deborah. Thank you. Layla, you're doing a really great job, Layla. Oops, sorry, Deborah. You're doing all right, too. See you.